Okay, so now we move on to section 5, the behavior of solutions. We've sort of seen so far in the mean value property and maximum principle section and in the energy method section, some discussion of the uniqueness of partial differential equations and the methods of solutions. Obviously, we constructed solutions which prove the existence. So in behavior of solutions, we sort of have the second part of regularity. We have the regularity at the start of a problem where you sort of have to even define what functions you're looking for solutions among. But then once you have found functions, perhaps they in fact have better properties than generic members of the class they belong to. And so this is what I mean by behavior of solutions. Perhaps there are stronger regularity results. And so let's begin with the regularity of harmonic functions. So harmonic functions, by definition, solve the Laplace equation. I don't think there's a particular point in the script where it says the definition of a harmonic function is blah, blah, blah. But I would make the definition that a function has to be twice continuously differentiable and obey the Laplace equation to qualify as a harmonic function. We've seen previously that twice continuously differentiable is necessary for the mean value property to hold, or is an assumption in our proof of the mean value property. So it makes sense to include it in the definition of harmonic function, but sources differ in this. So that's a harmonic function. We might want to consider, however, a different level of regularity. Oh, and by the way, the C2 is the one that makes most sense because the Laplacian is a second order operator, so you need second order derivatives, and so of course having twice continuously differentiable is somehow the natural choice for this equation. But suppose you didn't want to look for the natural choice. Suppose that you wanted to look for the most general choice. So you might consider distributions. So distributions that solve the Laplace equation in the sense of distributions. And of course, something is a harmonic distribution if its Laplacian is 0. All right, remember what that means. We'll talk more about this in the final section, but this means that for all test functions, u applied to the Laplacian is 0. Okay. And so what we need to do is we need to build up a little bit of theory for distributions if we want to say something about distributions. And in particular, we can extend the mean value property to distributions as well, and we call it the weak mean value property. Now, this is actually a really strange thing, the weak mean value property. You might remember this weird-looking function f here. The essential point, I would say, is what's discussed in exercise 27. So let's just have a quick look at exercise 27, which is about exactly these functions. And I would say the important point is to understand part D here. Okay, is that if you have a multiplier and you plug it into this sort of formula, that a distribution applied to such function approximates the spherical mean of the function. Okay, so the question you should ask yourself with the mean value property is, how do you even take the spherical mean of a distribution? And so it's a two-part answer. Part one is that distributions by their nature are somehow generalizations of integrals, right? We know this. And so what we need to do is we need to apply them to functions that approximate a sphere. And then with those two things together, then we would have the integral over a sphere, which we could use to define the spherical mean. So how do we find a function that approximates a sphere? Well, we take 0 infinity, right? We just take the positive half, and we take a test function maybe that looks like this, right? And this is our test function psi. And then we rotate it. So if we look in the plane now, we have our test functions psi, and we rotate it. right? So we have a little, maybe like this. My drawing's not the best. Like this. So we have a bump, but it's a circular bump like that. And obviously, as this becomes tighter, right, when it becomes more like this, something like this, it becomes a closer approximation to, in this case, the circle, right, to the indicator function on a circle. And so the idea is that if we act on all these sorts of test functions, then somehow in the limit, we are also acting on the indicator function for the sphere, right, as a limiting case. And that's why a distribution acting on a function of this shape should tell us something about, or should be the analog or the generalization of a spherical integral, integral over a sphere, and therefore approximate the mean value theorem. Okay, so that's almost everything, but we have this extra condition here in the definition of the weak mean value property. We don't just have like a bump function as I've drawn. What we have is we have a bump function that has two parts. So it has a positive bump and it has a negative bump like this. And so when you rotate it around, you'll have a positive sphere and, if you like, a negative sphere. Of course, there are other possibilities, but this is the main one to consider here. And so when you act the distribution on this orange one that I've drawn, what it will be like is it is as if you're taking the spherical integral on this minus the spherical integral from that sphere. And so when by acting a distribution on this function f, when the radial distribution has this property that the total mass is 0, is like taking the difference between the integral on two different spheres. And so we know that if we have a harmonic function, the spherical mean should be constant. And so the difference of two different spherical means should be 0. And that's exactly the weak mean value property, right? For all balls and for all test functions, so for all balls that lie in the domain and for all radial test functions psi, so that the positive part and the negative part are equal, the distribution is 0 for the derived or the consequent ring test function like this. And we have, so I would say a function has the weak mean value property if it obeys this. And then we have lemma 3.6, which is all harmonic properties, all harmonic distributions, that is ones defined as solving the Laplace equation, have this weak mean value property. Okay, so this is sort of replicating partly what we had for just ordinary functions, where all harmonic functions were shown to have the mean value property. Okay, so now this is where the real magic happens. The magic happens in Weil's lemma 3.7. In Weil's lemma 3.7, we proved that all harmonic distributions, in fact, are distributions that come from a smooth harmonic function. Okay, so every harmonic distribution U is of the form f of little u for some smooth harmonic function little u. Okay, I think this is perhaps the most difficult proof in the script. So let's just review the 3 steps that are involved in Weil's lemma. So the first part is to define, given a harmonic distribution, define a function u. Now this is actually a little bit tricky because in general, distributions do not come from functions, and distributions are not defined at particular values. So it's not clear, if you're given a distribution, how to make a function out of it. All right. But what we do is we consider the same formula, this special form of distributions on the space, Maybe I should call them like ring wave distributions or something, like this. And now we look at ones with a different normalization condition, namely that the radiuses or the radii obey that the total mass is 1. So these should be the generalization of a spherical mean for a harmonic distribution. So you define this function u to be the spherical mean of the distribution centered at x. So there are two things then you need to check. You need to check that it does not depend on r and that it does not depend on the distribution of the mass here. And both of those, which is what is exactly that, does not depend on the choice r and psi. That follows from the weak mean value property, right? That it does not depend on the radius and it does not depend on psi. So that actually does define now for you a function, u of x. So if you like, this is, you take u of x to be the spherical mean of the distribution. So that's step 1. Step 2 is now you should prove some properties of this function. Okay. What properties do you want to prove on this? Well, you want to prove two things. You want to prove that this function is harmonic, and you want to prove that this function is smooth. How you can prove that this function is harmonic is you prove that its distribution has the weak mean value property. The distribution u tilde corresponding to u has the weak mean value property, and you use that to show that u then also has the weak mean value property. And then because it's a function with the mean value property, it's a harmonic function. And to prove that it's smooth, you need a property, lemma 2.7, which is that the convolution of a distribution and a smooth function is a smooth function. Okay, so by definition, it's another distribution, but it's a distribution that comes from a smooth function. So by taking this averaging of the distribution, you get a smooth function, and because you know this distribution was harmonic, you end up getting that this function, derived function, is harmonic as well. So now we have two things. Step 1, we prove this little function u exists. Step 2, we prove this little function, little u, is smooth and harmonic. Step 3 is to show that the original distribution u is actually the distribution that corresponds to this little function, little u. Okay, and that's not immediately clear, but it comes from the fact that these are essentially modifiers in here. So there's some calculation to do. So those are the 3 steps. Step 1, define the function little u. Step 2, prove the function little u has the needed property. Step 3, show that the distribution is given by the defined function. All right. So that's the key idea. You, of course, should look through the details using the script and using the lecture videos. So what is the consequence of Weyl's lemma? So if you take a harmonic function, an ordinary harmonic function, which is C2, and you consider its associated distribution, its associated distribution is, of course, a harmonic distribution. And so, therefore, we know that that harmonic distribution comes from a smooth harmonic function. In other words, the function u, that you initially assumed only to be C2, is in fact smooth. It has derivatives at every order. So this is what we mean by increase in regularity. By only assuming that it's C2, we prove that in fact it's smooth. Assuming that it's C2 and obeys the Laplace equation, it follows that it's in fact a smooth function. So this is an improvement of regularity. Or to put this another way, there are no functions in C2 that solve Laplace's equation, but they're not also C3 or also C4. Right? So we can think about the functions in C2 as of course, the smooth functions lie in C2, but then there are also functions which are twice continuously differentiable, but not 3 times continuously differentiable. So I think, is it x squared absolute value x is only twice continuously differentiable, but not 3 times continuously differentiable, something like this. What it says is all those functions that are in C2, but not in the smaller subset of smooth functions, they can never solve the Laplace equation. All right. That's another way of thinking about this result. And in fact, any weak solution, so any distribution, you can imagine smooth functions or smooth distributions that come from smooth function as a subset of all distributions. And it turns out that if you look at just harmonic distributions, there's nothing outside that overlap. So that's sort of one way to think about the improvement in regularity, and it follows from Weil's lemma, which is this really cool result. But as I said, pretty tricky. There's also a bunch of miscellaneous other theorems for harmonic functions that describe the behavior of harmonic functions that I sort of grouped together here. Not only are functions smooth, but harmonic functions are analytic. This means at every point there is a Taylor series around that point that converges to the function. Okay, so we know some non-analytic functions. Maybe I'll go back to blue. Sorry. So non-analytic functions we've seen a lot. So for example, minus x squared. No, that's not. Sorry. X to the minus 1. All right. Or if you like, 1 on x, like so, for x greater than or equal to 0, and 0 for x less than or equal to 0. I think we checked this at the beginning, but not only is this 0, but every one of its derivatives is 0 at the point 0. So this is a smooth function, right? All its derivatives are continuous, for example. But at 0, the function is 0 and all its derivatives are 0. So the conclusion is that its Taylor series is 0. So at x equals 0, the Taylor series is just 0 plus 0x plus 0x squared, and so on. And clearly that does not converge this function, because this function is positive for small x greater than 0. So there's no neighborhood of 0 where the Taylor series converges to the function. So that's an example of a non-analytic function. Harmonic functions are analytic, which means they are represented by Taylor series, which means they are very easy to approximate and calculate with, and they're very nice, and so on. The proof of this follows from the representation formula, because the representation formula for a harmonic function is an integral over a sphere of a certain function, and that function is just effectively the inverse of a polynomial, and obviously the integral of the inverse of a polynomial, like the reciprocal of a polynomial, is an analytic function. So it follows from that. Really nice. We have Liouville's theorem, which is the only harmonic functions on the whole of space that are bounded are constant. All right. So you, for example, you might consider oscillating functions. All right. Oscillating functions are bounded or can be bounded, something like sine x plus y. All right. That's a bounded function. It can't be harmonic. So an intuitive reason for this is that we know harmonic functions can't have local minimum or maximums. And if you had an oscillating function, then it would need to turn around at some point to sort of, it increases and then it turns around and decreases to continue the oscillation. So that's forbidden. So oscillating functions are out. So the only other way a function could be bounded then is if it just grew really, really slowly. So the proof in the lecture script of Liouville's theorem comes from looking at an estimate of how fast or slow harmonic functions can grow, and using that to rule out the possibility that harmonic functions can grow really slowly and remain bounded. Either they don't grow at all or they grow too fast to remain bounded. All right, so that's Liouville's theorem. We also looked at this cool exercise in exercise 23, where again it's using this idea of bounded growth effectively. If a function is growing very slowly, then if you look at two large overlapping disks and apply the mean value theorem for balls on those two disks, the difference in the overlap, because the function is growing very slowly, cannot be so large. So therefore, the average value on those two balls has to be very close together. And if you take this for larger and larger and larger balls, you see that actually the difference between the function, the difference of the function between at 2 points, due to the difference at the value at each point is related to the mean value on the ball. Because the mean values have to be increasingly close to each other, it means that the values have to be increasingly close to each other, or have to be as close as possible to each other. In other words, equal. So if you look at exercise 23 again, I would say try to look at this through the perspective of what happens if you have a very slow growing function with the mean value property, and then you have the conclusion that it is constant. So that's just a nice theorem. And we also mentioned when we talked about fundamental solutions that this sort of tells you fundamental solutions or spherically symmetric solutions need to have a singularity for Laplace's equation. Okay, so this is lemma 3.4. I give it the name removable singularity lemma. So what do I mean by this? So consider, say, a function which is like x squared minus y squared over x squared plus y squared. So the absolute value of f is always less than or equal to 1. Right? You can apply some simple estimate there. So this is a bounded function, and it's not defined at x or y equals 0, xy equals 0, but it's bounded. And we know that this function, this is the typical function that does not have a limit. So this function has no continuous extension to 0, 0. So here's a function. Of course, it has an extension. You can just assign it whatever value you want at 0, 0, but there's no continuous extension. None of those extensions are going to be continuous. Likewise, or not likewise, completely the opposite. If you have a harmonic function on some small ball, except for 1 point, and it's harmonic and bounded in that neighborhood of that point, then not only can you extend the function to a continuous function, but it is a harmonic function. That is, it obeys Laplace's equation at that point as well, and therefore on the whole domain. So it can't have any singularities or holes that sort of look like this one. All right, it can have singularities, as we saw with the fundamental solution, where it blows up and becomes unbounded, but it can't have a bounded singularity like this one. So I think that's pretty cool. This can be useful for some time. We talked about, I think it's exercise 31 of this punctured ball, which sort of is an important counterexample to keep in mind for the Dirichlet problem. This sort of applies to that situation and helps you reason about that situation very nicely, this lemma. And then, so the last property, unique continuation. This, all analytic functions have unique continuation, so it's sort of a little bit redundant to add it here as a separate property. It just follows from the fact it's analytic. But there's at most one harmonic extension to a larger domain. So if you have a harmonic function here on some domain here, and you want to extend it to a larger domain, there's a unique way of doing this, or it's not possible. All right. So, for example, for the fundamental solution, it's defined on all of space except for the origin. There is no extension to the origin. It has a singularity there. It's equal to infinity. But sort of, if you like, similar to the removable singularity, if it does extend, then there is only one way to extend it. All right, this makes it somewhat like polynomials. All right, so that's just a random collection of other facts about harmonic functions. We also have some similar results, but not as many for the heat equation. You can prove many results for the heat equation and the wave equation and such, but that sort of that's going into physics, where you sort of start with a problem and then see what physical information you can derive about the problem in general. So we only just touched on a few of them. One thing that we did prove is similar to the Weil's lemma from the representation theorem for the solution of the heat equation. We can see that any solution of the heat equation needs to be smooth in T and analytic in X. So even if you just have, for example, a continuous function on the boundary, something like this, I think maybe there's even more general conditions. You can allow even discontinuous boundary value conditions, but I'm not sure about that. So go with what's in the script. So even just starting with continuous functions on the boundary, when you go forward in time a little bit, then the solution is in fact a smooth function. So the heat equation has this smoothing property. One way to understand this is if your initial value, if your initial value h looks something like this, then what do we know about the heat equation? We know that from the areas of high heat try to go to low heat, like so, and so the peaks become rounded like this, right, as time moves on, and it sort of fills in there as well. So that sort of explains why, because from it's moving from extreme values towards the middle, it sort of takes away the possibility of having sharp corners, and it becomes smoother over time. That's what I want to say. So that is, again, a regularity improvement, right? Only with the assumption of continuity on the boundary, then we get the smooth function for positive time, for example. So we also had a couple more things. We had exercise 36 that we spent some time on, and this sort of followed from the inequality among solutions. So this followed from, if you have sub-solutions to the heat equation, then you can get an inequality result between solutions to different heat equation problems. And we use that to show that if a solution of the heat equation, so a solution of the heat equation with 0 on the boundary of the domain, let's say for all time, then we use that to show that U goes to 0 regardless of initial conditions. All right, so no matter what the initial condition H was, you can look up the exercise 36. I think this applied to a bounded domain, and the initial condition had to be a continuous function. But for any continuous function over time, we know that the solution tends to 0. All right, and so therefore, if you have a steady state solution, you can look at the difference between those two, and the difference has to go to 0. In other words, the solution needs to tend towards a steady state solution if a steady state solution exists. So that's another type of regularity. Maybe you could compare that to Louisville's theorem, that there are only bounded solutions. Here, there are only solutions that are tending towards 0. Or maybe you would even view theorem 4.11, which is this uniqueness result. So for the heat equation with continuous bounded initial condition on the whole on all of space, there's at most one solution that does not grow too fast. All right, so if you look at this with the initial value of 0, then clearly 0, the function, u is identically equal to 0 for all space and all time, is the solution when the initial condition is 0. And it says that it's the unique solution that does not grow so quickly. Right. So in other words, if you compare this to Liouville's theorem, where if you have a function that's 0 and remains bounded, then it has to be, or it's 0 on some line and then remains bounded. It's a constant function, so it has to be 0 everywhere. Here, the assumption is not that it remains bounded. The assumption is even stronger, is even weaker, just that it doesn't grow super exponentially. Then there's at only this constant 0 solution. So that's a way to understand 4.11 as being similar to Liouville's theorem in its content. In that it's giving us the uniqueness. We could also imagine trying to use Liouville's theorem to give uniqueness, but it's a lot harder for Laplace's equation, so we didn't use it in this way. But we did for the heat equation. So that's for Laplace's and the heat equation. And I should say something, I guess, about the wave equation or about first-order systems. They don't have good regularity solutions. So we saw for the transport equation that the solution is just the translation of the initial condition. So clearly there, if you only have a C2 initial condition, then your function remains twice continuously differentiable or something like this, because the solution is just translation of the initial condition. There's no improvement. There's no improved regularity. And the same thing we see holds with the one-dimensional wave equation. We can also imagine a situation where you have two different waves, something like this, where you have a wave like this and a wave like this, part of the same solution to the wave equation, but this one is moving this way and this one is moving this way. And then you can imagine that maybe this one is something like this and this one is moving here. And you can imagine that when they move together, they can create some strange pattern. Or conversely, you can imagine that they start together really nice, but then they split into two ugly or two irregular parts. So there's in general no improvement for the wave equation or for first order systems. So that's why there's no slide for them here. And then that concludes this section with these random results.